Good morning, friends. At the outset, I would like to thank the organizers and the chairs for having invited me to speak on the unmet need, the genesis of an idea. I would take you through some self-illustrations as I go through the talk. Well, as all of us know, necessity is the mother of invention, and it all starts off when you get stuck in the mud. And the same thing happened to me when I first joined the educational institute that I am attached to. We started our postgraduate training in 2009, and I asked myself the question, was I ready to give my private patient to my student for learning PCNL? There are many other reasons which have resulted today in poor surgical training. So I thought that we need to buy a simulator. And when I found out the cost, it was around 1,30,000 USDs. And when I went to the office to discuss this with my boss, this is the way he reacted. So I realized that it was all about doing more with less because our healthcare finances are stretched out. Everyone would like to help the rich emperor, but the poor has to find his own way. We were not ready for the available simulators at that time because of the initial cost, the maintenance cost, and the dependency on vendors for services as well as spares. And so I turned towards the concept of DIY or do it yourself. It all started with a few sketches in 2012, and then we procured some raw material from the local available market. I set up my own workshop. Actually, I started using the workshop of my hospital. And this is the kind of simulator we first made with a manual design, which was cut out of acrylic sheets. And then we tried to practice on it after covering it with a piece of cloth. I soon realized that designing simulators this way would take a long time, and it was very difficult to actually materialize your idea. And hence I started learning computer aided designing myself, because in CAD or computer aided designing, we can actually design parts and we can see the parts moving on the computer before we actually go on to make a prototype. And thus this fluoroscopy based simulator was designed on the CAD afterwards. Various parts were designed. And thus I could actually see in the CAD how the simulator would look. And finally, this is how the simulator looks now as a finished product, where we can see at the top, it is a humanoid structure with a puncturing window in between. Now here, as we see, there are the fluoroscopy pictures of the kidney are mimicking the real kidney. The simulator has respiratory movements. No contrast is required. Any technique of puncture can be practiced. So to make these kidneys, what did we actually have to do? We actually had to make our own cast, learn how to cast silicone products in our casts, and then make our kidneys ourselves. In order to simulate the respiratory movements, I learned Arduino, which is a software coding system. Using the Arduino board, motor drivers, potentiometers, and some actuators and wiper motors, we could actually mimic the respiratory movements. So at the end of the project, I had made a simulator which basically helped the student to learn puncture. And so it was a sort of micro simulator. And I decided that we need to break the PCNL training into smaller training sessions using micro simulators, wherein each student would learn the small steps of PCNL on different simulators. And then at the end of the training program, we would try to integrate the knowledge gained by this micro training together. I thought that this would be a cost-effective training for the student. Busy nights after the operation theater spent in our innovation room, wherein we finally could make our fluoroless simulator. This simulator basically uses visible light in order to replicate C-arm images. One can puncture the pelvic calyceal system using any technique. This is a bullseye technique being practiced on the fluoroless simulator. I then developed an ultrasound guided simulator which allows practicing puncture through a gel using the ultrasound machine which is present in our clinic. A stone manipulation bench which helps track dilatation as well as practicing stone manipulation. So there is a silicone kidney inside which can be filled with an artificial stone, and then the student can actually practice stone pulverization and fragment removal. Thus, after developing these micro simulators, we now have a logic bench which helps the student to develop a three-dimensional anatomy towards puncture. Then we take the student to a fluoroscopy-free simulation station. We train him on the fluoroscopy guided station after that, ultrasound guided puncture, then track dilatation, stone manipulation, and then finally take him to the operation theater. So how do you do it yourself? Well, you need to first find out the problem, then think of a solution, then try to think how you would make the prototype, and then try out your prototype. The other commonly faced problem in our clinic was to get the female patient to do a uroflowmetry in the clinic, especially with the technician around trying to click the uroflowmetry on and off, waiting for the patient to pass urine. Invariably, the husband would come and ask, "Doctor, can she not do this test at home?" This unmet need was met with when my wife asked me, "Honey, can you fill the ice tray, please? We have guests coming at home tonight." And as I watched the ice tray getting filled was a stimulus for the next idea. So this is a CAD design of a meter in which urine comes into the first cubicle and then slowly overflows into the next cubicles. Each cubicle has a calibrated opening at the lower end, which helps urine to collect in the receptacle below. This was the first rather shabby looking prototype wherein I tried out whether the physics works or not. Then I realized that I need to adopt 3D printing. So I prepared the CAD design, sent it for 3D printing, and this is how the SLS printing of the uroflowmeter using nylon PA12 looked like. Initial tests were done on this prototype. And then this is the final product, which is now commercially available, which is an injection molded product. The third problem I would like to discuss here is we have a stone endemic belt here, and we found it very hard to break hard stones using the conventional pneumatic lithotriptor, which basically has a flat discoid kind of an end. I did some CAD designing and some stress analysis and found out that if we have a paraboloid lithotriptor, then the efficiency of the lithotriptor goes up many times. The same was published and now is being used by various pneumatic lithotriptor companies as their design. I'm fortunate enough that they recognize my name and print it on their brochure whenever they use this innovation. One day during breakfast, I realized that chicken sausages could be used as a prostate substrate and help our students to practice TURP. Now these sausages are being used in a silicone mold and our students practice TURP with these chicken sausages. So I had to learn a lot of chemistry here of forming materials, like here we see potting materials, rubber forming materials, and I used all these materials to form the mold of the TURP simulator. I started experimenting with wheat flour in the kitchen during the lockdown, and I prepared gluten in the kitchen itself. Then I used the silicone compounds to make a small mold here for the gluten. And this is the prostate kitchen. I was found one day evening baking this gluten into a prostate. So these are the various prostate products or the prostate formulas that I experimented with. I selected the best prostate consistency that I thought was suitable for HOLEP resection. And this is the HOLEP model. So this baked prostate basically is placed in the TURP silicone model, and it resembles HOLEP resection. We took a trial run in our operating room. So with all these simulators, we first did the Europad program, or the first simulation program using indigenous simulators at our center itself. It was a didactic lecture series followed by simulation and followed by live surgeries. The simulators were gradually introduced into the Euromed sessions, that is the simulation sessions of the Urological Society of India, and were highly appreciated by the overseas teams who came to see the simulators. We then did a national simulation program at the UCCON, that is Urological Society of India conference in 2020 in Kochi, which was attended by more than 90 faculties, and we trained more than 350 students. Happy to share with you here that simulation chapters have appeared in various textbooks. This is one example. So friends, if you want to do it yourself, you need to know quite a few things, as have been mentioned here, like CAD designing, Arduino, PCBs, silicon polymers, molds, 3D printing, experimenting with food materials, and last but not the least, using your own brain too. You need to be ready to be jack of all, learn as much as possible, adopt technology, and patent your idea, and more as you come across the obstacles when you start innovating and prototyping. Yes, as somebody has rightly asked just now, do I need to learn all of this? Well, if you want to work fast, you need to know at least something about each step as you take your idea from the problem to the prototype. This will help you to make your prototype faster, and at the same time will help you troubleshoot the problems that you face during prototyping faster. So friends, if you are in the field, you need to find the problem first, think of a solution, prototype, try it. When you're trying out the prototype, you'll face more problems which you need to think upon, find another solution, go around in circles till the hen lays a healthy egg. And yes, it is painful indeed. But yes, the pain is worth it if you want to own your idea. And this is a small list of the work that we could do as of today. So today, friends, I would like to thank you all. I would like to thank my team who have helped me walk up the odds. Without them and their persistence, it would not have been possible. Thank you all very much.